Before we move on to look at more algorithms, let us discuss the efficiency of linear search. How do we measure the efficiency? We will count the approximate number of steps linear search takes. In this algorithm, we are using one for loop, which means that if there are 10 elements in the array, the algorithm is going to perform approximately 10 steps. If there are 100 elements in the array, the algorithm is going to perform approximately 100 steps. Consequently, if there are 1 million elements in the array, the algorithm is going to perform approximately 1 million steps. With that in mind, we can see the pattern and generalize it to say that if there are n number of elements in the array, linear search is going to perform approximately n steps. To represent this, we make use of a notation called Big O notation. This is one of the most feared topics when it comes to algorithms, but don't worry, it isn't that scary. What does Big O represents? It represents the efficiency, or in other words, the running time of an algorithm as a mathematical formula. Big O notation is used to describe two things in an algorithm. Number one is time complexity. Number two is space complexity. Time complexity means how much time does an algorithm takes to complete. Space complexity means how much memory space does an algorithm takes. We won't concern ourselves with the space complexity for now and just concentrate on time complexity. So, based on these definitions, we are trying to answer the question, what is the big O for linear search? Or what is the time complexity of linear search? The answer to both questions is the same. Let's look at three possible scenarios for time complexity. We are going to find big O notation for each of these scenarios. Let's start with understanding what does the worst case scenario means in terms of linear search. Worst case scenario would be if we want to find a number that is at the last index of the array. For example, number 19. In this case, linear search is going to scan the whole array to reach the number 19. How many steps does linear search takes in this case? Approximately 10 steps, since there are 10 elements in the array. What about in the second case? This time we have 1000 elements, which means the linear search will take approximately 1000 steps to reach and find the number 19. What if there are 1 million elements? I hope you see the pattern. This is what a worst case scenario looks for linear search. We can generalize it to say that for an array of size n, linear search will perform n steps in worst case scenario. If we want to represent this using big O notation, then simply we will say big O of n. Next, let's take a look at what does the best case scenario looks like for linear search. The best case scenario would be if the number that we are trying to find is always the first element. For example, number 19 in this case is at the beginning of the array. In this case, does the size of the array changes the running time of linear search? If there are 1000 elements in the array and the number we are trying to find is the first element, linear search still takes only one step. If there are 1 million elements in the array, will that change? No. Linear search will still take only one step to find the element. Why? Because it exists at the beginning of the array. Based on this, we can conclude that it does not matter what the size of the array is in best case scenario, linear search would only take one step. How do we represent this in big O notation? We say big O of 1, which means constant time. This big O is saying that no matter what the size of an input array is, the algorithm will always take the same amount of time to complete. Let's take a look at average case. Average case scenario means that the element that we are trying to find can be found right in the middle of the array. This means that if there are 100 elements in the array, the number that we are looking for will be in the 50th element and so on. In this case, we can approximate and say that in an average case, linear search will take n divided by 2 steps. Now, in the big scheme of things, n divided by 2 doesn't really add any benefit in the running time. Therefore, we can just approximate it and say that in average case, linear search is also big O of n. To summarize this, the big O of linear search looks like this for the 3-time complexity scenarios that we looked at earlier. Generally, when we talk about time complexity of an algorithm, we are referring to the worst case scenario. Based on that assumption, we are going to conclude that the time complexity or the big O of linear search is big O of n. After every algorithm, we are going to do the same complexity analysis. This graph is going to come very handy. This graph represents different big O lines. Before looking into the graph, let us understand what each axis represents. The vertical, or the y-axis, represents time, as you can see on the top left-hand corner. The horizontal, or x-axis, represents the number of elements, as shown on the bottom right-hand corner. The graph line in the middle represents ON, or the big O of n. This says that as the number of elements grow, so does the running time. The horizontal line just above the x-axis represents the graph of O1, or the big O of 1. This says that no matter how many elements there are, the running time of an algorithm will remain constant. In the later lectures, we are going to look at the other big O graph lines.